Замечательно. Пить охота пить. Петь охота пить. Пить охота петь. Нет, ну. Проверяем. Незнакомый.
500.
Шлема, это самые штучки. Нам одобрено, а вам не одобрено. Представляешь, вот Нью-Йорке. Наверное, так же было в 50-х годах нашего века. Всего-то на все там. Мышей не лови. Не лови мышей, не лови лучей. Вот нет, понял, он тебя просто, да, видишь, сразу ехал, все, ехал. Ну, ладно, понятно. Ну, да, понятно. А что он не уезжает? Едет или что? Не знаю, там что-то не написал, да. Чтобы уехать.
Приглашаю вас на бесплатный не-вебинар «Мастер жизни». Расскажу, где найти энергию для новых побед, и как управлять своей реальностью, и как не пасовать перед проблемами. Если вы не понимаете, о чем речь, и в вашей жизни все хорошо, можете закрыть это видео. А если вам нужна новая энергия, если...
Welcome back to Science Click. Today, the symmetries of the universe. There are many complex laws that seemingly govern our universe. Conservation of energy, of momentum, general relativity, the standard model of particles. Yet all this complexity emerges from a deeper, purer concept, of which all these laws are only consequences: symmetry. In mathematics, a symmetry is a transformation which leaves an object unchanged. A sphere, for example, has a rotational symmetry. You can turn it around, change its orientation, and it remains the same. An infinite rope is symmetric by translation. We can move along the rope, it remains the same. It turns out that the universe can also have symmetries. A symmetry of the universe is a transformation that does not affect the laws of physics. To understand, imagine an empty universe in which we carry out a simple experiment. We throw a ball. Once released, it continues to move in a straight line at a constant speed. Now, imagine that we travel through the universe and carry out the same experiment but somewhere else. Here too, we observe that the ball continues in a straight line at a constant speed. It behaves in the same way. The laws of physics have not changed from one place to the other. This universe obeys a translational symmetry. We can move through the universe, perform our experiment in another place. The result is always the same. This universe obeys from one. It behaves in the same way. The laws of physics have not changed from one place to the other. This universe obeys a translational symmetry. We can move through the universe, perform our experiment in another place. The result is always the same. This empty universe also obeys a symmetry under rotations. We could have turned, changed orientation. The result would have been the same. Finally, this universe is also symmetric through time. We could have waited and thrown the ball a little later. The laws of physics do not change from one instant to the next. The fact that the universe obeys symmetries, that the laws of physics remain the same under certain transformations, imposes restrictions on the behavior of objects. To understand, let's go back to our empty universe and throw the ball. Once thrown, the ball acquires a forward motion, and at the next instant it is slightly further ahead. It has moved. But if we assume that the universe is symmetric under translation, that the laws of physics remain the same when we change position, then the situation is equivalent to the previous instant. The ball has moved, but the laws of physics remain the same there, and at every instant the ball therefore evolves in the same way. If the laws of the universe are invariant by translation, symmetry forces the ball to conserve its motion, which explains why it traces a straight line at a constant speed. Similarly, if an object rotates on itself, assuming that the laws of physics are invariant under rotations, at the next instant the situation is equivalent, and the symmetry will therefore force the object to conserve its rotation. Thus, to be respected, each symmetry of the universe imposes the conservation of a quantity, conservation of momentum for translations, angular momentum for rotations, and energy for symmetry through time. This principle is called Noether's theorem. Each symmetry of the universe imposes the conservation of a certain quantity over time. Noether's theorem also applies to the content of the universe, and in particular the quantum fields that make up matter itself. A quantum field can also present symmetries. The field of electrons, for example, is made up of complex numbers, and the laws of physics that describe electrons do not change if we alter the phase of all these complex numbers. To understand, imagine that we measure the altitude of an airplane on Earth. To express the altitude of the airplane, we must fix a reference level, for example the sea level. By fixing this reference, we can describe the altitude by a number. But this choice of reference is arbitrary. We could have chosen another level. We would have measured different values, but the physical situation has not changed. The same situation can be described differently, depending on the reference level we choose. In the same way, for the electron field, we can change the reference level. To understand, imagine that we measure the altitude of an airplane on Earth. To express the altitude of the airplane, we must fix a reference level, for example the sea level. By fixing this reference, we can describe the altitude by a number. But this choice of reference is arbitrary. We could have chosen another level. We would have measured different values, but the physical situation has not changed. The same situation can be described differently, depending on the reference level we choose. In the same way, for the electron field, we can change the reference level. which corresponds to altering the phase of all complex numbers, without this affecting the physical situation which is described. This change of reference constitutes a symmetry, and according to Noether's theorem, this symmetry also imposes the conservation of a quantity, the electric charge. Conservation laws, such as the conservation of energy or electric charge, are therefore not fundamental. In general, these quantities are not necessarily conserved. It is only when the universe presents an underlying symmetry that, in order to be respected, the symmetry imposes the conservation of a quantity. The principle of equal and opposite reaction are not necessarily conserved. It is only when the universe presents an underlying symmetry that, in order to be respected, the symmetry imposes the conservation of a quantity. The principle of equal and opposite reaction, for example, which boils down to the conservation of momentum when two objects separate, is only a consequence of symmetry under translation. If one object goes one way, the other must go the other way. Thanks to this symmetry, rockets can take off upwards by ejecting material downwards. However, a problem arises. Unlike the simplified example of an empty universe, our real universe does not appear to be fully symmetric. At a time scale of billions of years, for example, the universe expands, and it is therefore not perfectly symmetric over time. As a result, on a large scale, the energy of the universe is not conserved. Light, for example, gradually loses energy. Its wavelength gets stretched as the universe expands. The universe is not perfectly symmetric under translations either. It contains stars and planets, and is therefore not the same everywhere at this scale. Thus, if we throw an object, in general its momentum is not conserved. On Earth, for example, an apple falls downwards, it accelerates. Its movement changes over time because the situation is not symmetric. At first glance, our universe does not seem to respect symmetries. Even worse, the laws of physics appear to be different depending on the frame from which we observe. If we drop the ball inside a centrifuge, from the outside the ball seems to conserve its movement. But from the inside, the movement of the ball is not conserved.
Нет, если я так думаю, просто да.
Слишком ли ты недоумочный?
Ладно, вот, что-то вылетает на солнце.
It accelerates towards the surface. How can we explain that the ball behaves differently? The laws of physics are absolute. If we want a good description of our universe, we would like all objects, whatever our point of view, to always obey the same laws. When changing